Hello, my name is Mustafa. Welcome to Lab101. We'll be doing repeated measures ANOVA in this video. As you remembered, repeated measures is dependent in the as a variable. It has the time factor in it. So when you're working with time, you should do repeated measures ANOVA. Let's see the example here. So we're measuring cooling rate. These are temperature values, Celsius. These materials are here to prevent cooling. Metal, as you know, is the uh, least good amongst these three, and we have time as our factor. So we'll do repeated measures on ANOVA now. So assumptions: normally distributed. Let's see if it's normally distributed. I come to my calculator. This one, Smirnov test of normality. I stack my things on top of each other so that it's easier to copy. Bam. Wait, I cut it by accident. Let me copy. Nice. And like that. So it's easier this way, so that I can just come here and do it like this, paste it here. Let's see if they have normality. Bam, you have normality. How do I say that? I take my p-value, select my p-value here, and I p-value here. Yeah, right. And alpha, we know our alpha is 0.05. So if the p-value is bigger than 0.05, we accept a null hypothesis for normality test. The data is normally distributed. So we have our first assumption. And let's see if we have any outliers. I take my data again, copy it before I come to here. Descriptive statistics, percentile calculator. Put my data here. Let's see the percentiles. Q3 is 755. Q1 is 46. Q1 is the 25th percentile, and Q3 is the 75th percentile. I find interquartile range by subtracting Q3 from Q1, I find upper limit by Q1 minus interquartile range multiplied by 1.5, and I find my upper limits by Q3 plus interquartile range multiplied by 1.5. So I have no value over 60, so we don't need to worry about the upper limit, but the lower limit, we see that our one data, not variable, our one data is faulty, so we can remove it. But in this case, we say that we didn't meet the assumptions, so we'll do the non-parametric version of repeated measures ANOVA, which is Friedman test. I come to calculators. Friedman test, where is it? The problem with this, it doesn't provide the post-hoc. I'll explain what post-hoc is in a minute. First, let me do the test here. Come to here, paste all the values. Don't forget to check if you have any spaces. I already know we have spaces here, so I delete them. I'll calculate it, and P is smaller than 0.05. So what does this mean? ANOVA hypothesis, we know our alpha is always 0.05. It's smaller than 0.05, so we reject null hypothesis and accept H1. So there is statistically significant difference between the means of the groups. So we know that at least one of the groups is different from the 2 or 1. So how can we know? In t-test we know that we have two groups, so we know the difference in between is the two groups. But in ANOVA we don't know which groups are different from each other. So let me explain clearly. I'll take the averages. This is what the test does as well. It takes the averages. After, with some math magic, it determines if it's significantly different or not. So this one will be probably different from these two, but we don't know it yet. We cannot prove it with this value. We need to do more tests, like the t-test. We will compare these two firstly, and these two, and these two. So we'll need to compare the separate groups like in twos. But we already know that in one of these it will be different from the other two. I'm guessing this will be the different from other two, or this two will be different from this one. We can say that, but we cannot say it without a test. So unfortunately, we don't. We do the post-hoc test, test, but we don't have it in this calculator, unfortunately. So I come to here. I'll come to Kruskal-Wallis. You'll say Kruskal-Wallis was for non-parametric for one way ANOVA, but this doesn't matter because we're doing Bonferroni, which is general purpose post-hoc test, and this is used for Friedman test. So we'll be focusing on this one, but not the other values or the other data that will be provided. So I'm copying it here. If you can, if you want, you can write it like this: cotton, and this one would be metal and asbestos. Asbestos is a material that is put into walls, like to increase the to decrease the thermal conductivity within a building. And this is cotton, so you probably know that. I'll come to calculate. Again, it's normally distributed. That's not what we're looking for. I come to post-hoc tests. So what does this mean? Our post-hoc is, let me take a screenshot of this and come to my Excel so that it's easier. Okay, so our for group 1 met cotton and between group 2 metal, the difference is not significant. So let's come to post-hoc hypothesis. It's larger than alpha value 0.05. So we say that since it's larger than this, we accept H0. So there is no statistically significant difference between the two groups. So which groups are these? Cotton and metal. There is no statistically significant difference between cotton and metal. I come to the second one. Uh, the group 1 and group 2, we're testing that it's again larger than 0.05. So I accept the null hypothesis. There's no statistically significant between the two groups. So I say that group 1 and group 2 is same. They're almost same. And I come to the third part, group 2 and group 3. We see that group 2 and group 3 have a significant difference. See what I mean by comparing to the two groups? We'll have to do these to decide if these two is significant or these two are significant amongst themselves. So we see that there's a significant difference between group 2, group 2 and group 3. This is these have high conductivity, metals have high conductivity, and asbestos have really low conductivity. So this is what was expected. But the interesting part is cotton and metal don't have significant enough results. So we can say that, so that we cannot say these two are significantly different. So let me delete this part so that I can draw the graph of it and finally understand the full picture. I already took the means, so I'll write the means here. Means are here. and I'll take the standard deviations of the three groups, and STD samples. You should do always samples because you're generally working with samples rather than population itself. So you always do sampling. Take it there, then like this. This type of doing is wrong for repeated measures ANOVA. You'll probably have like for cotton. Uh, what, Normally what happens is that you have cotton and cotton trial 2, trial 2, and cotton trial 3. You have different measurements for these three. So you take standard deviations of each point. So I write mean. So you take mean, average. So you take mean of the three groups here, and then you take the standard deviation of the three groups like this, and then you'll draw it like that. But for this one, we don't have it, so I'm going to draw it like we're doing an independent samples ANOVA. So you would do a line graph like this, or a scattergram, but I'll do a bar graph to compare the means and show you what I mean by significance. Not like that, like this, and I take these as the labels. Insert, and it didn't take these as the labels. That's fine. Select data, edit, access labels. Okay. Now we have those. We don't need this. And I add my error bars like this. I come to plus error bars. I come to more options for series 1. It was asking for series 1. Doesn't matter. Custom, specify value. I delete one here. Select my 3 standard deviation values. Again, I'll do the same. Bam. I have my values like this. So let's compare these. So metal is, as you can see, is smaller than cotton and asbestos. When you're normally doing this, you want to have multiple trials for each group. So cotton 1, cotton 2, cotton 3, and you for metal, metal 1, metal 3, metal 2, metal 3, and for asbestos as well. You'll need to do those. Yes, that's about it. I also drew the line graph of it, since the bar graph was wrong. Bar graph shouldn't be drawn for this, so I wanted to explain with line graph. Normally you would have multiple measurements for these, so like you'll have one here, and one here. These are the same values. I just want to show it. You'll have your mean here, and you'll have your standard deviation here, like this. You'll drag it like down that, and for the other two, you'll have it like that. So you'll have mean cotton, standard deviation of cotton. When you're going to draw the graph, you'll use these values. So mean cotton, like this, mean cotton, and let me do for the other two as well. You're supposed to have like multiple measurements for it, but in this example we don't have them, so I'll put it like this. I just want to show how you would draw the graph of it properly. STD metal, mean asbestos, and STD asbestos. I copy the value from here so that it can. It doesn't copy the value. It copies like the equation that I put in. So for working quickly, you can do this value, copy the value, this is wrong, not like this. I'll select this one like this. Yes. And you would draw using these, place them next to each other like that. And this one as well. I don't copy it, I cut it with Control X on purpose. I take these values like this. Can I take it like that? Okay. I'll do it like this then. So asbestos here, metal here. This type of writing is important since you want to do it while you're graphing. You'll need to use these type of graphing. So I'll take these and I'll take these. How did I select it? I select normally with this one and just click on it and drag it so that you can select it, and then you press Control. I don't know what's in it for what would you do for Mac. I just know it for Windows. I press Control, insert, not a bar graph, sorry, line graph, the first one. You have your line graph like this, and if you want to add error bars to each point, you come to here, more options, mean cotton. You say mean cotton. For cotton, you'll need to choose the cotton one. Why did I put it like this? And I delete one. I select standard deviation for cotton. They're all the same. It doesn't matter. I repeat the process. I shake it a little bit. Plus error bars, more options, and I come to metal. I select it for asbestos, and it will give the values for these. Around here you can see that there's no significant difference. So how can we? I didn't put them yet, and since they're zero, there will be significant difference. But I don't want to like confuse you. I want to explain why the error bars are like put in like this. So the use of error bars is if they overlap for one series, like for metal, and asbestos and cotton, we have an overlapping here, so we know that there is no significant difference. So if the error bars overlap, we say the difference is not significant. And since we compared the means, we know it from our statistical test as well. So good luck on your internal assessment. We'll continue with independent samples ANOVA nextly.